Hello, everyone. Welcome to today's webinar on the SERDP and ESTCP webinar series. My name is Jennifer Nyman. I'm with Geosyntec Consultants, and I'm the coordinator of the webinar series on behalf of SERDP and ESTCP. The webinar today will consist of a brief overview of SERDP and ESTCP, followed by the technical portion of the webinar, which features Department of Defense funded research on groundwater hydraulic characterization and mass flux reduction. First, Dr. Chin Man, or Bill Mock from GSI Environmental, will describe the use of hydraulic tomography for subsurface hydraulic characterization. His presentation will be followed by a question and answer session. Second, Ms. Poonam Kulkarni, also from GSI, will discuss the use of physical barriers for managing chlorinated solvent source zones. Her presentation will also be followed by a question and answer session. We will conclude the webinar with a question and answer session with both of our speakers. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast platform. Firefox, Explorer, or Edge are the most compatible browsers to use. If you lose content on your screen, or if your screen freezes, try keying Control and F5 to perform a hard refresh. If you're accessing audio through your computer and you have difficulties, you can click on the arrow next to the Join Audio button and select Test Speaker and Microphone and follow the prompts as they appear on your screen. And if you continue to have difficulties with the audio, please call into the conference line shown here. Also, you can submit a comment using the chat box at the bottom of your screen if you're having any technical difficulties. The Q&A option at the bottom should be reserved for questions for our speakers. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You don't need to wait until the Q&A period to submit your questions, and in fact, we encourage you to submit questions in advance of that session. When you are submitting your questions, please do add your organization name at the end of your question so that we can identify you during the Q&A sessions. And with that, I would like to introduce Dr. Robin Neeson, the Program Manager for Weapons, Systems, and Platforms within ESTCP and SERDP. He is graciously filling in today for Dr. Andrea Leeson, the Deputy Director of SERDP and ESTCP, as well as the Program Manager for Environmental Restoration. Before joining SERDP and ESTCP, Robin worked at NAVAIR's Weapons Division China Lake in California. Robin?
Thank you very much, Jennifer. I'm very pleased to welcome everyone to today's SERDP and ESTCP webinar. SERDP is the Strategic Environmental Research and Development Program, and it was established in 1991 by Congress. It's a partnership between the DoD, Department of Energy, and EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program. In this program, we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts and development are conducted. There are 4 program areas in SERDP and 5 in ESTCP. The Installation, Energy, and Water program areas only in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapon Systems and Platforms are SERDP and ESTCP programs managed jointly by a designated program manager. Today's webinar presents results from research and demonstration efforts that were conducted under 2 program areas, environmental restoration and that's not correct, but okay. So this was resource conservation. Our webinar series highlights R&D efforts from each of the 5 program areas. Upcoming webinars will cover a broad range of topics, including sustainable coating systems for military platforms, SERDP and ESTCP efforts developing and demonstrating PFAS treatment technologies, and monitoring and treatment of groundwater contaminated with chlorinated solvents. You can find additional information about upcoming webinars at this link. And I'm a little ahead, I'm sorry about that. Okay, so this is the link you can find information about upcoming webinars at. And I'd like to remind everyone that a copy of today's session can be downloaded from our webinar webpage. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at the end of the webcast. And finally, I'm really pleased to announce that we will be holding a symposium. The SERDP and EST Symposium will be held again this year, beginning of December in Washington, D.C. It's a 3-day event and will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information is available on the SERDP and ESTCP website. I hope you enjoyed today's webinar. Back to you, Jennifer.
Thank you, Robin. It's now my pleasure to introduce today's first speaker, Dr. Chin Man, or Bill Mock, a Vice President and Principal with GSI Environmental in Oakland, California, as well as an adjunct professor at the University of Waterloo and Rice University. He has over 30 years of consulting experience in environmental, water resources, geotechnical, geological, and seismic projects. Stochastic groundwater flow and subsurface chemical transport have been 2 of his areas of research and practice ever since his doctoral studies. He is a licensed civil engineer, geotechnical engineer, and geologist, and he's a Rudolf Diesel Industry Fellow of the Technical University of Munich. He earned a bachelor's degree in civil and structural engineering from the University of Hong Kong, and master's and doctoral degrees in civil and environmental engineering from the University of California at Berkeley. Bill?
Thanks, Jennifer, for the introduction. My presentation today is based on a completed ESTCP project we completed in 2017 to demonstrate the usefulness of a high-resolution site characterization technique called hydraulic tomography. To start my project, I'll talk about the motivation of the work, the objective of our demonstration project, and our approach to demonstrate the technology at 2 sites. The study area of site number 1 is typical of a source zone in the orders of tens of meters. The second demonstration site is of a typical scale of a typical DoD facility in the orders of several kilometers by kilometers. And then I will discuss how the result can be used to develop a remediation strategy, especially for targeted remediation. And then I'll touch on the key factors to be considered when the technology is being considered to be implemented at the site. And then I'll summarize the conclusion of our study, the benefits to DoD of this technology. And then to end, I'll talk about some of the newer development on the technology. With that, before I start, I would like to acknowledge 2 collaborators of our ESTCP project, Professor Walter Ullman at the University of Waterloo and Professor Jim Ye at the University of Arizona, and their research group at the 2 universities. The motivation of the project, we know that natural system, for example, the figure shown on the bottom left on slide number 18, it shows a typical hydrogeologic system that are highly heterogeneous. And chemical fate and transport is mainly dictated by the heterogeneity in the subsurface. For example, the high hydraulic conductivity zones are typically preferential pathways. Examples are paleo channels, fractures in rock system, gravelly zones, etc. Those high hydraulic conductivity zones are preferential pathway for chemicals to migrate. And on the other hand, the low hydraulic conductivity zones Very often when they're close to the release area, they become a residual source that could be a source of contaminant for a pretty long time. And that's why high resolution site characterization is very important to have or to consider for successful remediation, so that we know where the chemicals are and how it's going to be migrating in the subsurface. To characterize the subsurface using conventional method, for example, using boring log, it gives you local information, and most of the time it gives you indirect information instead of hydraulic conductivity directly. For example, lithologic information, it may tells you between a certain depth interval, the material could be sandy or clayey. Still, it gives you a hydraulic conductivity information maybe within 1 or 2 orders of magnitude still. And a lot of times, geologists has to make interpretation between borings, between well logs. And sometimes if the spacing, if the distance are far apart, the interpretation could be subjective and uncertain. Sometimes could be inconsistent information. And in order to characterize the site in high resolution, for example, if you put in a lot of wells, like the one, the figure showing on the bottom right, it's going to be very expensive to install all those wells in high resolution. The last 10, 20 years, through the support of many research funds, including the SERDP research funding, our collaborator developed the hydraulic tomography technique for characterizing the spatial distribution of hydraulic conductivity. The concept of hydraulic conductivity is similar to the medical field, that if you generate a signal spatially and measure the response in different location, and by changing the signal sources in different direction, you're able to detect the information in between. Hydraulic tomography is based on a similar concept where you apply hydraulic stresses through changing the pumping or injection distribution in the system, and observe and monitor the water level response. And then all the information will be considered or analyzed at the same time, so that you get a 3-dimensional picture of the hydraulic conductivity distribution in the subsurface. And the approach we took at the for this project is we demonstrate the technology at 2 sites. For the source scale demonstration, we did that at the North Campus research site at the University of Waterloo, which is typically, and the study area is in the orders of 20 meter by 20 meter, and I'll get into the detail of that. The second demonstration site is a DoD Air Force facility, Air Force Plant 44 site in Tucson, in Arizona, and it has a study area in the orders of 2 kilometers by 2 kilometers. The first demonstration site, the North Campus research site, this is the arrangement of the wells. It is a 3x3 well network at the spacing of 7.5 meters spacing, roughly about 15 feet. Each well goes down to about 18 meters in the orders of 20 feet, 60 feet. And each well, they're equipped with multiple ports for measuring data, for example, water level, measurement monitoring. It can be used for groundwater extraction and injection as well. This slide number 21 shows a 3-dimensional depiction of the port, the configuration. Each port can be used for pumping or injection or for monitoring water level response. So in this case, we did a series of injection and pumping tests by pumping water from one of the ports and then monitor the response in the other. Some of the ports in the surface, in order to prevent drying up the port, we did injection test instead of the extraction. This is an example showing one of the pump test result. This example is pumping at the location in the middle, and the size of the bubble response represent the magnitude of the drawdown, the maximum drawdown we observe at each location. And by changing the location, the different depth at different ports, and also at different well location, we are seeing different responses. So this is one example. Some of the tests are shorter. When we pump from a more conductive zone, the response happened quicker. And some of the pumping test or injection test was through a lower conductivity zone. So it took longer time to get to the drawdown response. And altogether, we performed 15 tests, a combination of pumping and injection tests. This one shows the information when we calibrate the hydraulic tomography model. We use a subset of the collected data. In this case, we use 7 pumping tests to calibrate the model, and then use the result to look at the response for the rest of the test as a validation. So this one shows a good comparison of the simulated drawdown through the hydraulic tomography model versus the observed drawdown during the pumping test. And it shows a very good comparison. So when we consider the 7 pumping tests and invert the system during the hydraulic tomography, the result of hydraulic tomography give us a depiction of the 3-dimensional distribution of hydraulic conductivity. And in addition, we are using the transient information, so we obtain the spatial distribution of the specific storage as well. One nice feature or byproduct of hydraulic tomography is, in addition to the most likely distribution of hydraulic conductivity and the specific storage, it also gives you the uncertainty measure. So that information will be very useful for looking at the uncertainty or reliability of remediation. I will get into a little more detail about that. The uncertainty of the information basically is the uncertainty is reduced when you have measurement location, and the uncertainty become higher if you don't have any data. Next, let's look at the performance of the hydraulic tomography, the hydraulic conductivity distribution, and specific storage distribution as a result. The left graph shows the prediction of the rest of the pumping test using the delineated hydraulic conductivity distribution. The right graph is showing a similar comparison when the model is developed using geology information alone. So you can see that the information from hydraulic conductivity, hydraulic tomography, give you a better match to the validation test compared to a conventional model. Next, we also compare the delineated hydraulic conductivity at the well location versus the Permeameter measurement of hydraulic conductivity done at several locations. The light color line shows the result from the Permeameter measurement in the lab. And the solid line represent the inversion result from the hydraulic tomography. And in general, you see a reasonably good match with the distribution of hydraulic conductivity with depth. Then next, we look at the comparison of the geologic information versus the inverted hydraulic conductivity. This is a 3-dimensional, the one on the left is a 3-dimensional depiction of a geologic cross-section, and it is one of the sections, section DD. And also at the same time, we show the hydraulic conductivity obtained from hydraulic tomography in comparison with the geologic information. And it shows that they are also in general agreement. The next demonstration test is a larger scale. And here we use Air Force Plant 44 site. One of the reasons for using this site is the site already have a pump and treat system in place. So we can change the pumping distribution and obtain tomographic data for the demonstration. We install 44 pressure transducer across the site and monitor the water level response for about a year. And during this time, hydraulic pumping, the pumping distribution, injection distribution changes as needed during the 1 year duration. And the graph shows the distribution of water level response in one of the time snapshot. First, we did the two-dimensional analysis of the information to get a general picture of the distribution of transmissivity or convert into hydraulic conductivity. The graph here, the red color shows the location of the groundwater extraction well. The green color shows the location of the injection well for recharging the treated water. The yellow color shows the location of the monitoring well. The results show the hydraulic conductivity back calculated from hydraulic tomography is shown in the bottom graph. The left graph is the big picture showing the hydraulic conductivity distribution in the area of the graph shown above. If we zoom in more, we see more detail in the area when the density of wells become denser. And if we zoom in even more to the higher well density area, the information is in more detail. So hydraulic tomography gives you information that depends on the well density. The more well network, the denser the network you have, the more detailed information you obtain. And then the next step is we consider the screen interval of different wells. Most of the wells are screened in the upper unit, and then there is a equatorial unit in between. Some of the wells are screened in the lower unit, the upper zone lower unit. And we did the three-dimensional inversion and come up with the distribution of hydraulic conductivity in 3 dimensions. Next, we're going to look at the validation. During this time, we also identified a series of pumping response where the pumping has been steady for a while, and then we changed the pumping. So using one of the event as validation, this graph shows the prediction from the model. The black line is the actual measurement by the transducer. The red line is the mean of the is the water level prediction from the hydraulic tomography result. And the blue line shows the 1 standard deviation uncertainty estimate of the drawdown response. And you can see that the observed data and the mean prediction result are in good agreement, supporting the technical performance of the hydraulic tomography technique. And next, we're going to compare with the general distribution of the geological information we understand at the site. So this is the same result I showed earlier, the 2-dimensional depiction of the relative conductivity in the area. The red shows a higher conductivity zone. The blue shows a lower conductivity zone. And the hydraulic tomography result shows a low conductivity area in this region. And that coincides with the site understanding that the material here is less permeable. And that's why, as part of the remediation, hydraulic fracturing was done in this area to increase the conductivity at the site. And next, I'm going to talk about the result, how the information from hydraulic tomography can be used to design remediation and also develop strategy. For example, the hydraulic tomography result gives you the 3-dimensional distribution of hydraulic conductivity. Then you can isolate or look at the distribution where the high hydraulic conductivity zones are located. For example, here, the golden or yellowish color shows a higher conductivity area, while the blue area shows a lower hydraulic conductivity area. With this knowledge, you can design your pump and treat system. You can optimize the system where you can target your pumping from the high conductivity zones, or control the migration of the plume through a optimized pumping. And if you are using the information for designing a targeted remediation, for example, ChemOx or enhanced bio, you can use the information to decide where you inject the chemicals or the substrate in order to have a better delivery to the source zone. Or if you are designing a slurry wall system or permeable reactive barrier, then you can design your wall to key into the low permeability zone, or use a combination of the information to design a more reliable system. At the same time, if you are using it to monitor the changes of different remedy, you can look at the hydraulic tomography result before and after the augmentation to see if the hydraulic conductivity is changed during the remediation. And also, in addition to the depicted hydraulic conductivity information, hydraulic tomography also gives you uncertainty information, which could be useful to evaluate the reliability of your remediation design even before you do it. For example, you can generate Monte Carlo simulation of the hydraulic conductivity using the result from hydraulic tomography, and then look at the, let's say you do 1,000 simulation and look at your remediation design and see how many of them are successful. Then you can evaluate the reliability. For example, out of 1,000 simulation, maybe your remediation system is only effective for 300 of them. Then you have a reliability of 3.3 or 30%. So similarly, you can use that as a guidance to develop reliability measure. And also you can use the information to optimize your remediation using your best estimate, or alternatively, you can also define or design your remediation scheme such that you are looking for a remediation design that gives you the highest reliability or the highest probability of being successful, meeting the performance criteria. So to consider the hydraulic tomography, whether this is good for your site, there are a couple of things to keep in mind. One is, what is the objective of characterization? That dictates the resolution needed for the information for the hydraulic conductivity delineation. For example, if you are doing it for source zone delineation or source zone remediation, you might have a need for a higher resolution information. Or if you are doing pump and treat system, you might be able to live with a larger scale characterization. And also, it's very important whether you have existing well available for the hydraulic information collection. The existing well will save you money. Instead of putting new wells to collect hydraulic information, you can rely on existing system to give you the hydraulic response and perform the pumping test. And also another consideration is the cost of treatment with the treating the extracted water. If you already have a treatment facility on site, the extracted water can be treated without much additional cost. But if you don't have treatment facility available, you might have to put in some cost to account for cleaning or treating the extracted water. Or alternatively, you might be considering injection of clean water to generate the hydraulic signal. Another consideration is the operation constraint. So some of the site condition may not allow you to put in transducer. So that would be a consideration as well. If you have existing system, a pump and treat system, a monitoring network available, the additional cost of hydraulic tomography is very minimal. To summarize, we demonstrate that the hydraulic tomography is a very cost-effective, high-resolution site characterization technique, especially when you have an existing pump and treat system in place. And the information from hydraulic tomography will be very useful to develop a reliable remediation plan, or even for monitoring, for long-term monitoring. And at the same time, you can identify area where you have a large, maybe data gap, a need to further characterize the site. You can use reliability as a measure to gauge the value of additional information collection. The benefit to DoD with the delineated hydraulic conductivity information, each site can be, the information can be used to develop more reliable and targeted remediation, and also can help in defining long-term monitoring, optimized long-term monitoring plan. In the end, it will save remediation and monitoring costs and reduce environmental liability. To end, I'm going to talk about a couple of further development that we are doing with the hydraulic tomography technology. We are also trying out at 2 other Air Force sites demonstration with the incorporation of geophysical information, electrical resistivity survey to enhance the result of hydraulic tomography. One is at the Air Force Plant 4. We perform ERT to improve the result of hydraulic tomography. And at the Air Force Base, right now, we are doing tracer enhanced geophysics to look at the migration pathway. And in addition, we are incorporating flux measurement to improve the prediction, not just the hydraulic conductivity delineation, but also in the prediction of the flux, the groundwater seepage velocity measurement estimation using the technique. And also we are incorporating additional computational methods so that we can use any forward prediction model. So it's not just limited to the linearization technique that we have been using. So also that gives you the flexibility of using different type of measurement. For example, chemical concentration data, flux measurement, geophysical data, all can be in an integrated manner to improve the prediction. And also we are doing work to incorporate different geological material classification to further reduce the uncertainty of hydraulic conductivity delineation. So with that, I would also like to acknowledge my collaborator developing this computational technology, the group at the Technical University of Munich for developing some of the newer technology. So this ends my presentation today.
Wonderful. Thank you so much, Bill. We have received a number of questions. I would encourage the audience to continue to submit questions using the Q&A box at the bottom of your screen. To start off, Bill, would you please summarize for us how hydraulic tomography is different from conventional modeling and calibration?
Okay. In conventional modeling, a lot of time we use our geological information to come up with geological interpretation. For example, assuming that the subsurface is behaving like a certain layer system, and then use the geological information to define the layering system. In hydraulic tomography, is the other way. We don't define a certain zonation or pilot points like the conventional modeling. We let the data tell us what is the uncertainty estimation at each location. So there is no need to define different zonation or pilot point.
Okay, thank you. What kind of algorithm is being used for the tomography?
For the ESTCP project, we use a sequential linearization method developed by Professor Jim Ye, our collaborator. And also we are developing some of the technology. For example, the simulation-based approach that I mentioned is based on a different simulation method. One is sequential Monte Carlo. The other one is ensemble common filter. Right now, we're getting pretty promising results. So that it's not tied to any particular type of model. Any forward model can be used.
Okay. Is it necessary to conduct both groundwater extraction and injection for hydraulic tomography, or can it be performed with groundwater extraction alone?
It can be from extraction alone or injection alone, or as long as you have a way to generate hydraulic stresses in the area with different method. Professor Jim Ye also developed a method using river stage like when during rainstorm event, when you have flow in the river that changes along the river with time, that also create a hydraulic signal that changes with time. So as long as you have a way to change the hydraulic stresses in the area so that you can get the hydraulic stresses from different direction, you can achieve that tomographic result.
Okay. How much do the results change with the locations and density of monitoring wells? Are there guidelines for locating additional monitoring wells if that is necessary?
The rule of thumb is that in general, the scale of heterogeneity you can delineate is roughly about double the spacing of the well. So that's dictate the well density you need in a certain area. So if you are doing source zone remediation, you might need a denser well network, depending on the heterogeneity that you can see from, for example, the geologic information.
Okay, thank you.
Mm-hmm.
And what kind of resolution can be achieved with hydraulic tomography for the estimated hydraulic conductivity field?
The hydraulic conductivity field, as I mentioned, typically you can see a scale which is about double the size of the well spacing. So that's roughly the accuracy of the delineation of the heterogeneity you can see.
Okay, thank you. And can this approach be applied to fractured rock sites?
Yes, it has been applied to fractured rock system as well. Professor Ullman also have done a study in Japan to apply to hydraulic tomography to look at the hydraulic connection across the fault line. So that gives a very interesting result as well.
Okay, thank you. And if that site has a long history of pumping and injection operation and water level monitoring data, can that data be readily used for the hydraulic tomography analysis?
Yes, recently we have applied some system identification technique. Even though you have a long history of pumping data without a clear pumping test or a long period with a steady pumping, you can use signal processing technique to extract the transfer function or the unit response function from the historical measurement. One of the techniques we use for a Navy site is transfer function noise. So you can look at the dynamics and extract the unit response function from the historical measurement, even though the pumping has been cycling on and off irregularly over time.
Okay, great. For the characterizing of the hydraulic stresses, are they characterized as pressures or drawdown or something else?
For the stresses, we in the model, we put that as a pumping rate. So it's a Q, typically the same as your the way we do conventional modeling. But that also can be converted into pressure. So in addition, instead of being the pumping rate, you can use pressure as a control as well.
Okay, got it. And then we have a more specific question. When you were talking about the first demonstration site, and this is specific to slide 22, you showed a chart with some purple balls on it. And the question was, could you explain in just a little more detail what those represent?
Okay, so each pumping test, when we pump from a location, for example, on that graph, I think it's slide number 22, the gray color is the location where we pump. And then the bubble, the size of the bubble is proportional to the magnitude of the response at each location. So this is a general depiction of the response we see. For example, if you see a larger bubble, that means the connection between that observation and the pumping location might be more hydraulically connected. So in here, we're showing a larger bubble in well CMT2, while the pumping as PW1 in one of the zone, I think it's zone 4. That means the connection between these two locations is stronger. So when you change the pumping location, you will see a different distribution of the bubble. So that means it's an indication of how well is the connection between the pumping and the monitoring location.
Okay. Thank you very much, Bill. And at this time, we will move on to our second speaker. Bill will return at the end of this webinar to answer additional questions. If you have more questions for him, just indicate that on the Q&A box. We'll be focusing on some more general level questions at that time. The second portion of today's presentation will be delivered by Ms. Poonam Kulkarni, an environmental engineer with GSI Environmental in Houston, Texas. She has over 12 years of experience in engineering and environmental consulting and has served as co-principal investigator on multiple DoD-sponsored research projects that apply innovative strategies to characterize and treat conventional and emerging contaminants in groundwater. These include the development of an innovative enhanced bioattenuation technology for DNAPL sites, characterization of the nature of PFAS, methods to evaluate and reduce variability in groundwater monitoring data, as well as a demonstration of passive soil vapor extraction technologies. Ms. Kulkarni earned a bachelor's degree in chemical engineering from the University of Texas, Austin, and a master's degree in civil and environmental engineering from Rice University. Poonam, thank you.
Thank you, Jennifer, and welcome everyone. So the goals today are to discuss some of the benefits of flux reduction barriers, show some capabilities of an Excel-based toolkit called the Source Barrier Tool, and present results of the small-scale demonstration using a new application of permeation grouting that comes from the geotechnical world. Now, stepping back a bit, there was a State of the Science review conducted as part of SERDP Project 1740, where the authors concluded that because of matrix diffusion at these chlorinated solvent sites, there's more mass in the subsurface than thought. It's harder to remove, and it persists for a long time, which makes the implications for remediation pretty significant. They also noted that although difficult to project, that they foresee more containment projects as the end state, using conventional vertical barriers and hydraulic containment, as well as innovative technologies such as flux clog. And so this project focuses on flux clog, or flux reduction barriers, which have two key benefits. And the first is physically reducing the mass flux of contaminants leaving the source zone, and a lesser known advantage of increasing the degradation or NSCD rate. And this is because the influx of electron acceptors like oxygen, sulfate, and nitrate that's carried with groundwater flow can consume a large fraction of the available electron donor at a site. And so by diverting these competing electron acceptors, we can create an enhanced reductive dechlorination zone. And so overall, this technology has the potential to provide long-term treatment of source zones where the mass flux is greatly reduced, back diffusion is managed, and attenuation rates within the source zone are increased. Now, overall, the vision for this demonstration was really to adapt methods from the geotechnical world, where they use permeation grouting that allows grout to flow into the pore space where it can then gel or harden. And the remediation business also has a lot more experience with injection technologies over the last couple decades. So the goal was to apply these grouts using our standard injection technologies to see if we can implement barriers more effectively. Now, in preparation for the field demonstration, we did a lot of background research on all types of barriers, including permeation grouting, and wanted to crystallize all this knowledge in one place, which became the Source Barrier Tool. And so this shows the main user interface of the toolkit, which runs on Excel 2016. Now, the toolkit has several modules with resources to help users evaluate the potential benefits of a barrier, which includes, for instance, mass flux calculations and tools that can calculate source biodegradation rates or visualize the concentrations within and outside a source zone over time using a modeling example. It also has several modules that show which characteristics and barrier types are feasible for a specific site. And finally, it has some additional resources for understanding historical applications and flow through heterogeneous soils. This slide shows a screenshot of the 3 different modules that can help quantify the benefits of a barrier at a particular site. So first, the mass flux calculation refers to the ESTCP mass flux toolkit, as well as the ITRC guidance document. And the second module, you can quantify the expected flow reduction. And the third module, you'll get to the biodegradation benefits calculator. Now, one key thing to note here is that the increase in biodegradation would be applicable to type 1 sites, which is fairly common for DoD sites where a fermentable oil or other electron donor is released along with the chlorinated solvent. And so the biodegradation benefits calculator can take general site-specific information, barrier properties, and concentrations of the key electron acceptors, both up gradient and within the source zone, to calculate a potential increase in biodegradation rate of that key CVOC. So to put this into perspective, Dr. Newell published a paper in 2004, which estimates that for a typical chlorinated solvent site with electron acceptor diversion, there would be a potential increase in NSED rate of about 500 pounds per year. Next, these 4 tools can help users evaluate the feasibility of installing a barrier at a site. The site suitability page, for instance, walks a user through some key questions about a specific site. So for this technology, the best suited sites are the ones that are late-stage chlorinated solvent sites with low remediation potential. The site should also have some ongoing biodegradation in the source zone, with preferably a confining unit underneath. Also, recharge may be a concern at some sites, so those with either low recharge or some type of cap may be best. To evaluate this in particular, an infiltration or recharge calculator is included. And finally, evaluating access becomes important, and the barrier visualization tool and technology comparison can be useful for this. So for instance, typically slurry walls and sheet pile walls are proven technologies that are commonly used and can create pretty tight barriers with wall hydraulic conductivities on the order of 10 to the -7 or 10 to the -8 centimeters per second. Permeation grouting, as I'd mentioned, was the focus of this project, is less common, but has the potential advantage of being more flexible in terms of barrier placement. It requires a smaller working area and being able to be used with injection-based technologies. It's also more applicable for higher permeability sites, has a depth limit of about 40 feet, and can create wall hydraulic conductivities of about 10 to the -5 centimeters per second. Now, the barrier visualization model shows groundwater flow paths generated using ModFlow of various configurations, indicating what variables and designs can lead to the most effective flow reduction. So a square or completely encapsulated barrier, for instance, is much more effective with a 97% flow reduction. A more surprising finding was that groundwater flow paths wrap around more tightly than expected, which is why a single wall wouldn't be very effective and would only reduce groundwater flow by about 9% within the source zone. Finally, a couple additional resources in the toolkit include a survey of historic studies, and this is coming from an EPA guidance document, as well as sites evaluated from the California GeoTracker database. And there's also an evaluation of the distribution of groundwater flow in heterogeneous media, which I'll talk about next. For this particular study, we looked at different rules of thumb regarding groundwater flow. So for instance, Payne says 90% of the aquifer flow is transmitted in only 20% of the cross-sectional area. And we were interested in these rules because the idea was that if you could just clog up that key 20% of the cross-sectional area, you may be able to have a significant impact in reducing the groundwater flow. And so we looked at 43 sites from GeoTracker and analyzed 141 boring logs in total. For each boring log, we tabulated the soil type, its thickness, and typical hydraulic conductivities to look at what percentage of flow goes through each layer, as you'll see on the figure on the left. And the graph here on the right then shows the cumulative total groundwater flow on the y-axis and the cumulative aquifer cross-sectional area on the x-axis. Each boring log here is represented by a single line, and overall there's a large distribution of geologic settings in this data set. And so the very heterogeneous ones are the lines on the top left, and the more uniform geologies are closer to the 45-degree diagonal line. And if you take the average of all the curves, the key point is that approximately 90% of the groundwater flow goes through about 30% of the aquifer cross-section, which is pretty similar to the original rules of thumb. Switching gears now to the field demonstration, we wanted to see if we can apply permeation grouting from the geotech world into the remediation industry using commonly used injection techniques. And now there's quite a bit of literature on this application where silica gel grouts are usually used to either strengthen soil or decrease the permeability of soil for water tightening applications or groundwater control. Sodium silicate also has the advantages of being chemically benign and has a controllable gel time that can be adjusted and is resistant to both chemical and biological degradation. So this is a conceptual diagram of the permeation grouting process, where first a direct push rig is used to install multi-level injection wells for even distribution of the grout. Then a mixing and injection skid is used that combines sodium silicate with an electrolyte or hardener. In this case, we use dibasic ester, and an inline mixer combines the two solutions right before injection. Once injected, the solution changes from a liquid to a gel, typically on the order of about 1 to 3 hours. And finally, you can repeat this process by installing closely spaced injection wells around a source zone, creating a barrier. Now, before getting to the field, we tested 2 different types of grouts. The first was a standard sodium silicate grout, and the second was a vegetable oil formulation created by Bob Borden's team at Solutions IES that has the potential to provide a slow-release electron donor, which could increase the degradation rates within the barrier. Now, these grouts have controllable gel times based on the mixing ratios of the sodium silicate and electrolyte. And we even tested a simple salt, but then found that dibasic ester and inorganic hardener had more reliable and consistent gel times. And so the final formulations consisted of about 10 weight percent sodium silicate, 2 weight percent dibasic ester, and for the solution on the right, an additional 5% of emulsified vegetable oil. This is an overview of the small-scale demonstration where the goal was to create 4 barrier cells using the 2 different grout materials. And each of these were created by injecting into multi-level injection wells in the center that spanned about a 20-foot thick zone. So overall, we wanted to gain experience with the materials, the mixing, and the injection process. Now, this demo was done at the Indian Head site in Maryland in a clean area. And the site generally consisted of about silts and clays and was on the low end of the applicability of using sodium silicate grout at about 10 to the -4 centimeters per second. Here we have some pictures of the equipment and injection skid. On top, we have the 2 mixing tanks that created the sodium silicate and dibasic ester solutions, along with a large water tank here on the right. An inline mixer was then used right before injection. And as you can see in the pictures on the bottom, the injection manifold had 12 different lines where the grout could be injected simultaneously. So the mixing process in general is a bit more complex than standard injection-based remediation projects. And this is because the injection skid needed to mix 3 fluids at very specific concentrations. It also needed to deliver multiple locations at the same time. And we also wanted to ensure that the grout didn't harden within the skid before we injected it. We finally also did some on-site gel tests using actual site soils, which showed that both grout types gelled with gel times around 2 to 2.5 hours. After the injection and grouting process, we conducted a constant head injection test in the cells. And after solving for aquifer parameters, compared the hydraulic conductivities to previous slug test results. This graph shows the final results where we achieved about a 64% reduction in hydraulic conductivity. Then there was some consideration for applying this at a larger source area, but because this area had even lower permeability, it was decided that a barrier may not be feasible to install and show enhanced degradation within a reasonable time frame. To conclude then, because of matrix diffusion, these chlorinated solvent sites are more difficult to treat, which may mean a comeback of containment technologies. Installing a barrier around a source zone can have two key benefits. First, it would reduce the mass flux down gradient of the barrier, and it can reduce the influx of competing electron acceptors, which would increase biodegradation rates within the source zone. Also, the source barrier tool can be a resource for evaluating if a barrier may be applicable at a specific site and to compare the different technologies available. Finally, in this first application of using permeation grouts with injection-based technologies, we reduced an already low permeability zone by about 64%. Overall, some benefits to the DoD include the source barrier tool, which is available online and can be run on Excel, permeation grouting, which can be another tool in our arsenal for barrier placement, and finally, a refinement of this heterogeneity rule of thumb that can be applied to other injection-based technologies where 90% of the groundwater flow occurs through about 30% of the cross-sectional area. And with that, I'm happy to take any questions.
Great, thank you, Poonam. Just another reminder to our audience, please submit questions through the Q&A box at the bottom of your screen. We do have a few questions for Poonam that we will ask. First, in the toolkit, is there cost information?
Yes, there is. So there are planning level costs for slurry walls and sheet pile walls. This is coming from programs like RACER, as well as EPA guidance documents. And for the permeation grouting portion, the costs are based on our field experience from this project.
Okay, perfect. And could you just explain again at a high level, why was the slurry wall not installed as part of the demo?
Sure. So the idea was really to try to adapt methods from the geotechnical world into our remediation industry. And so some of the disadvantages of slurry walls are that they require a larger space. And so we were thinking that if we were able to install these closely spaced injection wells with grouts, that we'd be able to get a more cost-effective solution without any of the waste generated that you usually would.
Okay, thank you. And does it work just as well for injection grouting then to use just one very long screen instead?
That's a good question, and I think our thought process on this has changed a bit. So because of this heterogeneity rule of thumb, the original idea was that if we could just clog up that small cross section with a long screen, for instance, that we would get the majority of groundwater flow. But after a little bit more consideration, I think we were thinking that the water would maybe back up, and so you would still need kind of targeted multi-level injection wells to get the entire vertical distribution of flow. And so the short answer, I think multi-level wells would be a little bit more reliable in terms of getting that consistent vertical barrier.
Okay. And can you comment on regulatory acceptance of the approach? Are you aware of some sites or where regulatory approval has been indicated in terms of chlorinated solvent source zones?
That's a really good question. Not that I'm aware of right now, but I can definitely check and get back to whoever if they want to send me an email.
Okay, sure. And then is it necessary to pump water out from within the slurry wall?
So at some sites, it may be required, but the idea was that with permeation grouting that we're not clogging up the entire vertical transect. And so even if you get a 90% reduction, these barriers become a little bit leaky. You would need to evaluate the infiltration and recharge, which is Toolkit has some calculations for. But if you are applying permeation grouting, the idea is that you wouldn't need to, but it should be evaluated on a site-specific basis.
Okay, thank you. And can this general approach be applied in fractured rock?
Not that I'm aware of. I'm not sure you would be able to get a consistent barrier. So from the research that we've done, we haven't seen any applications in fractured rock, no.
Okay, thank you very much. And at this time, we would like to bring back Bill, and as mentioned before, we'll ask a few more higher level or general questions of each of Bill and Poonam. To our audience, do feel free to continue to submit the questions, your questions if you'd like. Bill,
Sure.
Since there are so many high resolution site characterization techniques, what is your opinion about how a manager might go about selecting the most appropriate one?
It depends on the objective of the characterization. So, for example, if the goal is to obtain more flux information, then doing high resolution flux measurement might be a better, might be a good approach. So the bottom line is, if there is a way to incorporate all the information together, that will give you the best shot. For example, each method will focus on getting a specific type of information. So you can, one of the approach is to use data fusion or integration to combine all the information together to reduce the uncertainty of the overall characterization.
Okay, and could you expand on that at all, Bill, in terms of integrating the data, more specifically addressing how a site manager might decide whether additional data might be needed and what would be most useful?
For example, if you start with the boring information, you might be identifying some area with some uncertainty in the interpretation. Then you can supplement with geophysical measurement to get the larger scale characteristic. And then if you need to have hydraulic information, for example, hydraulic conductivity distribution, for defining your treatment, like what I presented today, then hydraulic tomography will be give you the information you need. And then statistically, you can also combine them in a coherent manner so that the result, the uncertainty from each test can be reduced, and then you can consider the overall improvement in the uncertainty and find out which one will be more beneficial to fill in the missing information you need for the remediation.
Okay, thank you. Next, we have a question for Poonam. Are there any new technologies on the horizon that you think might be amenable to adaptation to form barriers?
Sure. So on a similar theme of adapting some tools from the geotechnical world, there's this new method called the grout bomber. It's this massive machine, almost like a sewing machine, that can install basically like grout columns in a really quick pace. So with some of our experience in the past, we've gotten anywhere from about 80 to 150 vertical columns of grout installed within a day. And so if you can quickly kind of stitch these grout columns around a source zone, that may be another option. It hasn't been tested for barrier technologies per se yet, but it definitely sounds promising so far.
Okay. And also for Poonam, one last question. Can
Sure.
permeation grout be implemented in proximity to foundations or other subsurface structures?
The geotech world, actually, they do apply them near foundations. We don't have experience with it currently, but I have heard that it can be done.
Okay, thanks. And then as we're wrapping up the webinar today, what is the last message that you would like to leave our audience with today about the topic that you presented on? One last takeaway, and Bill, we'll start with you.
The takeaway is that high resolution characterization is a very important information for remediation. So try to decide for each site what is a good way to obtain the information to the scale that you need to come up with a reliable remediation design.
Okay, thank you. Poonam?
Sure. So the takeaway message, I think, is that because of matrix diffusion, these chlorinated solvent sites are a little bit more difficult to remediate. And so containment technologies may make a comeback. We, of course, have previously used technologies like slurry walls and sheet pile walls, but now permeation grouting may be this additional tool in our arsenal that we've adapted from the geotech world using our standard injection technologies. And so just another option, another tool for managing these sites.
Okay, great. Thank you to both of our speakers today for the very informative presentations and for answering all of the questions. Our next webinar in this series is on Thursday, October 31st. It's in the Weapons, Systems, and Platforms program area, and it is on developing and demonstrating non-toxic and sustainable coating systems for military platforms. Registration is open for this webinar as well as the other webinars that you saw earlier, so please visit the SERDP and ESTCP webinar webpage to register. And before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. And we would appreciate it if you could take a moment to please complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you.